So this is lab 4, and our objective is to analyze the spring mass system by comparing experimental data from a video to a model output and then modeling the energies involved. Our results, they were that the difference between the spring mass's motion from the video and the model motion were minimal, and that the experiment fulfilled the energy principle. Overall, the data from the video and the model data were consistent with what was expected. Physics concepts, we have the spring, mass, and the Earth to be our total system. We are assuming that the mass of the actual spring is 0. The fundamental principle, or at least the first one, is Newton's second law, which is the sum of the forces basically can be used to predict the motion. Forces involved include gravity from the Earth pointing downwards, force exerted by the spring pointing upwards since the spring is stretched. We have the energy principle, of course, which is the change in energy is going to be equal to 0. No work done by the surroundings because of our choice of system. We have the potential energies, which are the Earth and the spring, and the kinetic energy, which is due to the motion of the mass on the spring. This is a snapshot of tracker. You can see a graph of the y position of the mass, which we use as our point of mass. Calibration was used from the attachment point to the mass in one frame. We have the initial position of the mass to start out the motion and the actual mass. So for the spring force and beyond, we need L naught and K. We can find K if we know the period of oscillation. The period of oscillation can be found using the y position data, and we know the mass, of course. So we use the equation to find K, 6.86 Newton meters. The system is initially in static equilibrium since the mass is at a velocity of 0 and it's not changing. So the absolute value of the force of the spring is going to be equal to the absolute value of the force of gravity. Rearranging this, we can solve for L naught. And of course, L naught is the relaxed length. We found that to be 0.126 meters. K and LO are put into the code along with the mass, the starting velocity, which is 0 because of the static equilibrium, of course, and the starting position. And this is the code and analysis. So from what was discussed earlier, we can model the motion by the net force through Newton's second law, and the net force can be found through the sum of the spring and gravitational force vectors. SL and L hat have to be updated for each iteration since they are changing. This is a video of the model. And this is the model versus tracker graph. So the red is the experimental data from the video on tracker that we imported via CSV. And the blue, of course, is the model position. So we found those to be pretty close. We have the energy code and analysis. So we had to, of course, add in the energies that are involved, as discussed earlier. So from the equations that we laid out earlier, we can find the kinetic energy, the potential energy due to gravity, and the spring potential energy. And we can find the change in all of those through each iteration. And then we can graph all of these together on one plot. So we have delta K, delta US, delta UG, and then delta K plus delta US plus delta UG, which, if you can guess, is the total energy. And so this is what we got. The blue line is delta K. The red is delta US, which is dependent on whether S is increasing or decreasing. The green line is delta UG, depending on whether the Y position is increasing or decreasing. And the yellow line is delta E. So, what does it mean? Well, the energy principle is satisfied because delta E is found on the graph to be around 0, or a straight line on the x-axis, since there are no surrounding objects doing work, as noted before, With that said, delta E would not be that close to 0 if it were not for the small delta t, meaning more iterations increases the preciseness of the data. Because when I use a larger time step, we notice that, or I noticed that the line of delta E was kind of around 0, and that maybe the average was 0, but it did not actually stay consistent with the x-axis. And as discussed earlier, the oscillation period for y was 1.52 seconds, and for x it was 1.61. These are close, even though y is displaced more from the relaxed length than x, because the net force on y is smaller with gravity and the spring working against each other. So with a smaller net force, that causes less change in motion, less acceleration. So it's not going to be moving as fast, which means it takes longer for a full oscillation. However, the only force, thus the net force in the x direction, is just the force due to the spring. So that is it.